So greetings of the day, and now we are going to see 5G measurements at UE. Basically, UE and UE. I mean to say mobile or onboard unit or something like that. Okay, devices. Okay, those devices and base stations will be usually measured at laboratory level in order to ensure that its operability is fine. Okay, so what they will measure is that they will measure for different parameters. Okay, so there are for example, if you have an antenna, you need to evaluate what is the radiation pattern of the antenna. Based on vibram, from that you can able to evaluate gain, beam width, and fast null beam width. So several parameters, and also S parameters, VSWR, impedance matching. So apart from that, polarization and uh, so many things can be measured. Similarly, for UE, all the whole system level, because the UE is system kind of thing, because it has antennas, amplifiers, power amplifiers, low noise amplifiers, and basically receiver chain, transmitter chain, and so SIM card, and many things are available. So each will have its own testing. Apart from on top of that, so each one will have its own testing. Finally, they will integrate as a system, either as a UE or a base station. And so on the system level, it has to perform, it has to comply with the certain parameters, because apart from each component each component will be tested at different stages for its own parameters that may not be straight away checked over here, but when they are integrated as a system. Okay, after that, so we have certain parameters, like that is defined by regulatory compliance body, like 3GPP, ETSI, and some of the regulatories based on the country. Okay, like Japan has a TELEC, and Korea has KCC, and similarly China has its own standardizing body. So they will have some stringent conditions on top of 3GPP. So either device, if you want to sell in those countries, your device or UE or mobile or any onboard unit or whatever on base station, whatever it may be, it has to comply with their spec. Okay, otherwise we cannot sell. So earlier we used to call, for example, in India it is if you want to sell your product, you have to have ISI marking. Okay, so that's a similar way. So okay, for products they have some different standards. Okay, that's what we are going to look into now. And so in this 3GPP spec overview, and so device validation process, some of the how the device validation being done, which means different parameters, and how it's being done, and some of the parameters and its unique characteristics. Okay, but we are not covering entire parameters, but I'm covering so some of the key parameters. Okay, and summary. Okay, and these are my references. Okay, so there are plenty of 3GPP specs are available on the online 3gpp.org. Okay, you can go through that. Okay, but I have covered from some of these spec. Okay, but some are from online contents. Okay, thank you. 3GPP spec point of view. See, if you want to, for example, if you are working in if you want to validate your 5G UE, right? So you need to have for example RF perspective. I'm talking RF perspective. Okay, RF perspective or a protocol perspective or RRM perspective, you need to refer these specs. Okay, for example, so what these specs are actually saying is that what all these specs are saying, what it says is that, for example, what are parameters need to be verified. Okay, it will be called as test cases. Okay, test cases. And so each of the parameter, how it will it will be how each test cases are being defined. So everything will be discussed in these kind of things. Okay. So for example, 1, 2, 3, 4 is there. So one is talking about range 1 and standalone FR1 conducted test, FR2 radiated test. So 2 in 2 means that is 38521-2 talks about FR2 radiated tests. 3 talks about FR1 conducted and FR2 radiated tests. Okay, and performance requirement. The 4 talks about the performance requirement standalone, non-standalone, FR1 connector. So these are all the descriptions. Okay, and 38523 is that your protocol performance. So it's a protocol based thing. And 533 radio resource management, and NSA, SA, NSA, FR1 connected, something like that. Okay, 38810, but basically I think we have seen in the last presentation. It is basically talks about study on test methods. Okay, and so you can go through some of these specs, and then you can see different test cases being defined there. But this will talks about how you want to measure, like we have mentioned in the last presentation, that how OTA will be looking like, how do you what are the procedure to be followed to test any test case. So something like that it will be there. Okay, so the detailed description, what is all about the setup, what setup we should have, and how it should be mounted, assembled, and everything, how so detailed procedure will be there in this spec. Okay, like for EMIC, or for example standard for example, some of the products they used to get standardized. For example, FCC, IEC, IEC, and there is a civilian standard, military standards. Some other standards are available. If you want to sell your product to military, you need to follow those. You need to comply with that IEC and FCC. Those kind of things in that military standards are available. So there they will mention each and everything. So how what are all components to be there, and then how it should be measured, and many things will be mentioned there. So okay, so now device validation process. Okay, device validation process. So device validation workflow will be, okay, the initial device validation workflow will be, first we have to do compliance testing. And there are 3 components are available. If you want your product to be certified by the regulatory body, like like now test certification body, like GCF, Global Certification Forum, or Omniair, or different certification bodies are available. Okay, they will have their own requirements. For example, they may accept with the 3GPP alone, or they will say that no, if you want to sell your product in Japan, you have to comply with the TELEC, otherwise we cannot certify your product. Or TELEC will say no, if you are okay, on top of the 3GPP you have to comply with these requirements. For example, that will not be too much deviated from 3GPP. 3GPP like a common minimum requirement. So on top of that, they will define for certain parameters. For example, I am defining ACLR to be 3GPP is defining ACLR to be minus 30 dB and the out of band. Okay, but they will define minus 40 dB because their environment is different and many things are different. So similarly, and the channel power, they will say that this should be this much, and like that. So they will add a few parameters, or they will have some difference in the values of the parameters. So those kind of things will be there, but it will not be too much deviated. And also they will define that, okay, what equipment you have to use for measuring these parameters. So that's what they will do. Okay, and so compliance testing includes RCT, RF conformance testing, RRM, radio resource management testing, protocol conformance testing. Okay, and so this has a workflow which is the compliance testing has. Initially, we'll develop the test cases using coding. Okay, what the development is? What, see, we have to do we do manually, right? For example, if your antenna is there, you will go and check the in the earlier days, what they will do, if you want to capture the radiation pattern, what they will do, so they will rotate the antenna. I think we might have done in the some students might have, if you are a student, or if you have graduated already, so you might have done in the microwave lab. So you rotate the horn antenna, then note the reading. You rotate the horn antenna, note the reading. Okay. Then finally you will those will plot those points in the graph, polar plot. Then you will see the radiation pattern. But now what is happening? So they have automated systems. You just mount your antenna and then you enter the button in the run the software in the some PC, control PC. Then you can see that the whole radiation pattern is in your hand in 5 minutes, okay, or sometimes in 2 minutes, okay, depends upon the resolution what you are setting, okay. So that is automated mode, okay. So that is what they are being done here. So for example, you are connecting the device, you are going to measure this particular window, you are opening that window and capturing the data, and at this point this parameter to be set. So like that we are setting it manually. But in the development, what will happen is those parameters will be done in a fraction of seconds, and then it will be done in a very fast manner. It's a kind of automated testing. Next is that pre-conformance testing. So once you developed, then we will do a lot of testing on that. Okay, we will see whether it is working properly or not, like a development. So automated sequence and everything is fine or not, whether U is responding to all these test cases or not. And final, then we'll go for conformance testing. So conformance testing will be validated by someone else. And then regression testing means, see, one test case is conformance, one test case is already tested, and separately, okay, separately each test case are being tested. Then finally we have to see pre-conformance means, so it is a one test case level, okay. Then conformance means what? So okay, so test case module by module we will check in this one. Okay, conformance means we will check, okay, test case is working fine. Okay, for example, if I have taken ACLR, adjacent channel leakage ratio, test case is working fine. Okay, we are getting the values, results as expected. So everything is confirmed. Now regression, what will happen? So we will run at a time many test cases. Regression means it's a repetition, and several times we will measure the see whether we are getting any fault or not, because it should be repeatable. For example, I am testing one at one point of time, it is working fine, then I left, that's all. Later point of time, if I test that, there may be there should be a value difference will be there. For example, I am getting sometime 36.2 dB. Okay, next time if I measure 35.8 dB. Next time it will, if I measure 36.4 dB. So there should be a deviation will be there, should be there, because repeatability cannot be ensured, because a lot of equipments are involved, uncertainty is involved, so many things are involved. But that deviation should not be too much. So that we have to ensure. So that's why we do regression. And also it will be done with the other test cases. For example, you have developed 10 test cases. So at a time all 10 test cases will be tested. So in order to ensure any one test case is failing because of the regression, okay, because when you do it alone it is working fine, but when you are doing in regression maybe sometime it may fail. So then that time we have to find out the root cause, okay, because some procedure you are following in one test case, another procedure you are following in another test case. So when it gets merged, when you are doing that merged, it should be not be any problem, but sometimes we may get problems. So that's why we have to ensure this regression. Then acceptance will be done by the customer, okay. So test solution vendor will give to us a team like a test house team, or OEM team. They will see the acceptance test. Test house team means, for example, SGS is there in the China, and okay, GCF will have certified labs, several certified labs. So they will buy these solutions, and then they will see, okay, where your log, they will check your logs and then see, okay, yeah, that's good, and everything looks fine. Then when they say acceptance, then that's all. So this is called as compliance testing, okay. So GCF will not only do this alone. GCF will not only look for this alone. They will have another testing is called field trials, okay. So once your laboratory level, it's okay, fine, okay, great. Then they will go for field trials, okay, because laboratory level it may work very good, but field trials it may fail. So how UE is behaving, or a device is behaving in the real-time environment. So what they will do is, for example, if you are testing your device, what they will do, they will fix the maybe that's my gut feeling that, okay, they will fix the node B at one position, and then they will keep your UE device at some certain position. They will roam here and there, and then find out what are all they will capture all these parameters, and then see, okay, yeah, it looks good. So field trial also, it's getting passed. For example, if you are taking protocols, means on the lab you might be getting very good results, but when you are setting into the field, but it's not complying with that. So because in the laboratory environment you will have a channel emulators, okay. So there you will emulate the channels what is present in the environment, okay. But when you get into the field trials, there you will see different environment, okay, like almost, because that is all measured, but still you may get some deviation. That we need to ensure that deviation should not be too much, okay, because anyway we cannot mimic entire exact environment as like in the channel models, because it's approximate models, that's all, okay. So though they are measuring several measurements, after that only they are formulating the channel models, as we discussed in the last presentation. Like they will measure each and everything, okay. So each and every scenario, for example, buildings, multi-storage buildings, and trees, and tree scenario, and they will have mirrors, concrete walls, and several scenarios they are making, and then they are finally based on the data available, they are formulating the models, okay. I like a Friis transmission formula, okay, like Rayleigh fading or ray chain fading. So several fading methods are available. So but some more models also we discussed a lot last time in New York University, and several models, okay. And so but it may not be exactly fitting into the environment, because that we cannot ensure, because climate keeps changing and everything is changing. So for example, when I tested multi-storage building, that time 4 blocks were the four for example, if I'm going to same location, when I tested that time it was 4 floors. Now it has become 8 floors, okay. So that we cannot ensure, right? So that's why a field trial is being done. So but there we have to see how much deviated is this, okay. Next is that interoperability testing, okay. Interoperability testing. So interoperability testing is that interoperability testing is that we'll have so as we discussed in the last presentation, you will see when you are going into the network, you will see a lot of equipments with the different OEMs. For example, Node B will be someone, for example Nokia, and core will be Ericsson, and then antennas will be Andrew, that is Comscope now, and so you will see cables will be Andrew, or RFS, or some. So you will see mux will be different, and so you will see different operators. But those OEMs will develop their products based on the common spec only. Say for example, so 3GBP or some spec only, but still we have to ensure that whether it is interoperable, because whether it is communicating properly with the other OEM vendors, OEM equipments or not, that we need to ensure. So that is called as interoperability testing. So upon doing these 3 testings, then you can ensure that okay, your product can be validated successfully, and you can your product can be certified to sell in the commercial market. So that's what the GCF and many global certification forum. If you go into the www.gcf.org.com, you can find a lot of information on this, okay, because device validation, and what all devices being recently validated, certified, or what all the devices can certify, where they can sell your product. So several informations are available, okay. Next is DUTs, okay. As I mentioned before, can be G node B or E node B or BTS, UMTS, Utron, several things, okay. Or UE. AE can be it can be mobile, 5G mobile, 4G mobile, or CV2X device, anything. Onboard unit, for example, if you are looking for autonomous car application, for example, if your device is looking for autonomous car applications, then onboard unit will be there. Or if you are looking for uh, like a military based IoT based military applications, then you have to test on-board unit. Okay. And so there are the 5G test beds are available. So if you want, for example, 5G test beds also, they will get certification from they will get, a license from the GCF that, okay, we can test these products. So then GCF will provide license to them, so that, they can validate the certain products, and then they can, come for GCF certification. They can come for a certification. 5G testbed, what they will do is they plug in with the new equipment, some equipments, okay, for example, Node B or UE or whatever it may be, and then they will test each and every product. For example, if you are design and amplifier, then you can plug in your amplifier at that particular stage, and then you can test. Okay. And if you are having, Node B stack, layer 1 or layer 2, layer 3, anything, so you can test, whatever you want. So that's what is the test bed is all about. I think India also, you might have heard, like 2 years back or 3 years back, they proposed the 5G test bed. I think massive work is going on. I can see that, several times the requirements are coming on 5G test bed, and based on which I am talking. So some stacks developments also going on. So, and I can see that in some of the website, some 5G test beds, IIC, IIT Kharagpur, IIT Kanpur, several people, I can see that several everywhere I can see that. So several stacks development and many things are going on. Okay. And testing is going on, and several components also being developed and indigenously developed in India. So it's a massive effort is being going on. Okay. And measurement setups. Okay. Next is measurement setups. It's basically conducted mode and radiated mode that we mentioned in last presentation. So device validation and introduction. So greetings of the day. Before we move on to device validation introduction, we need to see some of the specs. Okay, that will give you an overview of what I have been talking about. As I mentioned before, the spec will dictate the measurement setup as well, which component to be used, or what are different component to be used, or what are different equipments to be used. Okay, for example, you can see here a system simulator, and then this is the UE under test. Okay, and you have a splitter, circulator, all these components are available. So this is for particular test case. Okay, some of the diagrams may be common for all the kind of thing. So you can see that some of the test cases require this much complex setups. You can see here several system simulators need to be used. Okay, and you can see here some of the scenario needs fader scenario, fading scenario. So which means when you apply fading, then what is the response I am getting at the for example, in terms of throughput, in terms of power, or what power reduction I'm getting, so while applying the fading. So those kind of stuff can be measured. Those kind of test cases will be measured by employing these kind of setups. You can see here AWGN, so AWGN and other things. So AWGN now is also being added here, splitter, so several components, and this is called as a combiner. Okay, here it's getting splitted too, and then it's getting combined at here, and then so why we use for combiner? Because in order to handle the multiple inputs. Okay, you can use it to two-way splitter, 1:2 filter, 1:3 filter splitter, or 1:4 splitter. Okay, so splitter, what it does is, see, in general, if you talk in terms of power, splitter, what it does is, for example, you are giving input as 20 dB. Okay, so you will get half of the power in the one port, or half of the power in the other port, for example. So 20 dB means you will get 17 dB each. Okay, so which means 3 dB less. 3 dB means what? I think one of the lecture I have mentioned that 3 dB means 50%. Okay, if you take 10 log of 0.5, you will get it around 3. Okay, so that's right. So this kind of diagrams are available. So there are so many diagrams. So you can see here that. So in the spec, where they will mention which diagram to be referred. So you have to refer, for example, this is the spec for test cases. So this is the spec for diagrams and other things. 36508 will also talk about several algorithms and other things, other features. Okay, so you can see here these are all the test cases. So Initially they will give introduction, and then you can see here, this is the test case which I was talking about. Okay, you can see here 6222G1, and you can see here maximum power reduction, maximum output power reduction. This is the test case. Okay, here what is the purpose we are going for testing. Okay, everything is mentioned here, and where it should be applied. So for example, power class 2, 3 devices can be applied. So you can see here release 15 and forward. This is actually 5G spec. Okay, I think I have mentioned this spec in the beginning of the presentation. And so what should be the channel bandwidth, what is the relative channel bandwidth, and other things for FDD, TDD bands, and what will and you can see here. So we are in this test case, we are testing maximum power reduction. So what sort of reduction we can expect? For example, for QPSK it should be less than or equal to 1 dB. Okay, and for QAM, because system as modulation order increases, the limit also will increase. Okay, that it should be less than 1 because the modulation order for QPSK is 2 bit. Okay, here we are handling 4 bits. Okay, and 6 bits. Okay, so as modulation order increases, the power reduction also would be increasing. Okay, that's what is looked at here. And you can see here, see what should be the RB start high, what should be there. So those kind of stuffs being covered here. Okay, and initial condition, what should be set before we move on to the testing. So they will talk about attach, detach procedure and other things. So what format we have to use, those kind of stuffs will be mentioned here. For example, you can see here they will measure a configuration of PDSCH, PDCCH. All these parameters would be defined in this particular annexure of this particular spec, and those parameters can be read from there. And you can see here, so here you can see that climatic conditions. Okay, test environments. So normally we use normal environment, but some of the measurements should be done. So some of the stringent measurements should be done for all the. So here what they mean, normal means it's a normal temperature and normal voltage. Here temperature low, voltage low, temperature high, low, voltage high, and temperature high, voltage low, and temperature high and voltage low. Okay, so these kind of stuffs, this kind of, under this environment condition, how UE behaves for different frequency bands and then different values. Okay, different whether it meets the required specifications. So those kind of stuff can be have to be verified when you run a test case. Okay, that's what is the test case is all about. Okay, so you can see here, so test frequencies, what should be there, low, high range. Okay, and what bandwidth, so lowest bandwidth, the highest bandwidth. So for example, if you take about CV2X, it is lowest bandwidth is 10 megahertz and will be 20 megahertz. Okay, but here in 5G it will be varying from 5 megahertz to up to 400 megahertz. I think 250 megahertz is being already been, I think on pipeline, but 400 megahertz yet to be implemented. I think that's what I know. And test subcarrier spacing, but in CV2X we use 15 kilohertz carrier spacing, but and also LTE, but in 5G it is very much flexible, because we have 15 kilohertz to 20, because 2 power n into 15 kilohertz. Okay, 15 kilohertz is the base. Okay, into 2 power n. So when order n0 means it is 15 kilohertz, n1 means it is 30 kilohertz, n2 means n is equal to 2 means 2 power 2 4 into 15 60 kilohertz, and then 2 power 5 means, so it will be I think 32 into 15, it will come around, I think 240 kilohertz, something like that. Okay, so those kind of things are there. So whether we want to follow lowest or highest, it's a relative value. We have to see based on permitted subcarrier spacing. For example, if the permitted subcarrier spacing is 120 kilohertz, 15 kilohertz to 120 kilohertz, then lowest is 15 kilohertz and highest is 120 kilohertz. But if you are having highest as the 240, so that we need to verify before we move on. Okay, and these are all the condition for power class 2, power class 3, class 2 devices are nothing but class 2 devices, class 3 devices with the power, maximum power, output power of as action channel power of Class 3 is 23 dBm plus 23 dBm, whereas class 2 it is I think plus 26.1 dBm. Okay, so based on the power level they classified the devices. Okay, power handling and output power, maximum output power, they are device classified the devices. I think in FCC or IEC standards, okay, you might have seen class A commercial. Class A means, so for example, military devices. Class B means it's a commercial device, and class C means it's medical related devices. So based on that, they will set stringent conditions. Okay, in order to see, for example, if I am if I am going to produce devices for class A, for example, military application. So I have to have my product has to undergo several testing, which will be highly stringent, as I know. But civilians, commercial devices will not have much. Our devices will not have much. Our will not have much. Commercial devices will not have that much stringent. Yeah. Okay. So. So we have been discussing about power classes. Next is the test procedure. Okay, test procedure also will be mentioned. For example, so these are all the parameters to be tested. For example, CPU, FDM, GPSK, all these things to be tested. How many RB? Everything is information will be given in the spec. If you find several RAN meetings will happen every that I have mentioned before. So each RAN meeting, what they will do is, if someone finds some mistakes in this, then they will amend this in the next release. Okay, so I think every 6 months or 3 months, I don't know exactly. So it happens. RAN 86 I think recently happened. So after that they release the new versions. For example, you can see here it is G20 now. Okay, so every time it will keeps on changing G number. So you can find out in the 3GPP spec website. Okay, for all these changes. Okay, you have to keep a track of 3GPP website, so that these things are not missed out. Okay, and test procedure you can see here. So system simulators and the uplink scheduling information, uplink HARC process. So for what format to be used, what RNTA is to be used. So everything will be given in that. Then command control, up command means maximum power. So the power is set to be maximum power. Okay, and so what we want to measure, we want to measure main power of the UE. That's all. Within the for a given channel bandwidth, we have to measure the mean power. Okay, that is average power. Okay, so this is what is the test procedure, and you can see here. So the values limits are given here. So in the test case code during development time, we used to we have to take care of these things, limits. So if your measured mean power is within this tolerance, then that will be in the test case will become pass. Otherwise, it will be fail. It will fail. So the test case fail may be due to it can be due to test solution, or it may be really due to the UE itself. So that we have to investigate the step by step. Okay. So we have to follow several, we have to analyze several logs, and then finally dictate the what is the root cause of this issue. So those things and all, it will go on to and fro. Okay, it will be going multiple iterations. Then finally you will make this test case pass. Okay, that's why I have mentioned about similarly as the 38512 will have a different set of test cases. Okay, here you can see that the part 2 range 2 standalone test cases will be there. So here you can see each test case, for example 6 to 6 series is there. So minimum output conformance, maximum output conformance. So transmit power for uplink MIMO, and transmit power for carrier aggregation. So see that power itself, you are going to measure only power, but different scenarios. Okay, the one is that one is for carrier aggregation, the other is for uplink MIMO. Then several uplink and output power dynamics for say carrier application, uplink MIMO. So several scenarios will be followed. But you will be ultimately measuring only one power value, but for different scenarios. That is the beauty of this each testing and all. And you can see here, for example, UE maximum output power. So here test purpose, everything is mentioned. So what should be the maximum EARP can be found, and then those informations are given here. So what is the maximum ERP in these, for this band? What should be the TRP, total radiated power, and what should be the EARP, if aromatic isotropic radiated power. So similarly, you can find for other test cases as well. So everywhere we are measuring, what we are measuring? We are measuring, either power or throughput or modulation quality, all those things, but for different scenarios. Okay. So what we are going to measure in this 5G scenario, you will be measuring EARP, TRP, and other stuff. But based on by analyzing the signals, we can able to find out EVM and ACLR, adjacent channel leakage ratio, and error vector magnitude, spectrum flatness, and then carrier leakage, outer band, occupied bandwidth. So so many things are there, but for different scenarios, carrier aggregation, and uplink MIMO. So several things are available. Transmit signal quality, for example, frequency error. That is one of the test cases. What is the quality of signal? So they can be measured using the frequency error, because if frequency error is the measured frequency error is, it is to beyond certain limit, then it means your design is not proper. So then we have to check the RF component level and many things. Okay, you can see here in transmit modulation quality. Modulation quality means ultimately this EVM come into picture. Okay, error vector magnitude will come into picture, and carrier leakage will come into picture. In-band emission will come into picture, because these are all modulation quality. So if modulation is proper, okay, and then you will not get the error vector magnitude beyond certain limit. Okay, and so the emission within the band will not happen. Okay, and so this kind of stuffs can be measured. So similarly, as I mentioned before, so you can see here the same frequency error they are testing for carrier aggregation scenario, as well as the uplink MIMO scenario. So this is how it will progress. Okay, and so this is what I was mentioning about this. These parameters only will be measure will be let me project this screen. So these parameters, the whatever I have discussed now, so those parameters only will be mentioned here. Okay, will be done here. Okay, so pre-conformance. So development, first we will do development, then we have to see all the test cases are running or not. So if we find any problem, and then we have to analyze here and there, and then to and fro will be going on, because different teams will be, protocol team involved, L1 team, L2 team, L3 team, several teams will be involved, and physical layer design team also will be involved. So everybody will be involved. If test case through, then it's okay. So they will analyze we have different teams will analyze the logs, and then finally they confirm that okay, it is conformance. Okay, and then we'll go for regression and acceptance testing. Okay, so that's what is I wanted to tell. Now device validation introduction. Okay, now so test components with the basic capabilities. Okay, validation introduction, I think I have covered so many of the test cases and all. So how it should test cases are required, defined, and then what is required for each test case, that those things and all we have already covered, but still we'll cover. And so one is test components. So why we go for validation? One is so it should have some basic capabilities. Okay, otherwise that device is not fit for commercial launch or military launch or medical launch, whatever it may be. Okay, so some of the parameters to be measured. Okay, because that it's the device is, if it is not working properly, it is not serving the purpose of itself, and also it is disturbing other equipments. So that also we need to take care. So the thing is that, for example, your device is not working for your function, that doesn't matter. Okay, that doesn't matter, but it should not affect. If it's not working, then it will go within that device itself, but it may affect the other devices also. Sometimes what happens is your device will do a fantastic job, whatever is defined for that particular device. Then it will start interfering. By the time it will start interfering other networks. Okay, sometimes you can see that several crosstalks will come into picture. You will be calling someone else, but someone else will pick with the call. And sometimes even I faced whenever I have BSL phone. So there sometime I used to get interference from other network operator, so that I can smell, I can sense that one. So because your BSNL device is working properly, but other operator devices are not working properly because it is interfering the BSNL devices. Sorry, BSNL network equipments. So those things and all we have to be very careful, and then we have to measure those kind of things. So that's why test component with the basic capabilities. So they have minimum requirements that I have been mentioning several times. Minimum requirement. First such thing is ACLR, adjacent channel leakage ratio. Okay. And second one is channel power. Channel power should come first. I don't know what has happened. So channel power. Basically, first we will check for channel power, because within our band what is the power being transmitted. Next is ACLR. ACLR means we will look at the for example this is the your bandwidth, desired bandwidth. Okay, and first what we will look for channel power. Channel power is what is happening within this band. Okay, is the band. Okay, there will be some guard band will be available within that band. Beyond that, within that band, for example 50 RB if we have, okay, for 10 megahertz, for 15 kilohertz thing, 50 RB 15 kilohertz subcarrier, you will have a 10 for 10 megahertz, it is 50 RBs. Okay, there 2 RBs will be guard band, I think. Okay, 48 RBs only. No, I'm sorry, I think 5 RBs will be guard band RB. Okay, and 2 RBs will be allocated to the control. So 48 RBs will be allocated to the for the data data transmission. Okay, and ACLR, what we will look for, what is happening in adjacent channels. So what is whether this power getting leaked over here, which means what it will bring down the performance within the band itself, because we may be happy that okay, if it goes, what happens, but you are wasting your for example, if you are supplying 10 dB power, okay, 10 dB power has to be utilized within this band. Okay, if you are leaking for example 1 dB power, then you are only utilizing 9 dB power, and also you are disturbing the side band, adjacent band also. For example, if you are working in intelligent transport system, ITS, okay, that is a CV2X band. Okay, I think yesterday I saw that 5.9 gigahertz, and think FCC has voted for Wi-Fi and automotive CV2X. CV2X. I think there was voting happened for to allocate the 5.9 gigahertz for CV2X, and then for Wi-Fi. Okay, so when two technologies are working very closely, when the guard band is very limited, bandwidth is very limited, band spectrum is very limited, that time and all, if you are leaking into other channel, what happens is it will affect the other vendor also, other application also, or other network, or whatsoever you want. Next is combined cumulative I think a common distribution function. I think this is especially for 5G, and we will measure the distribution function for when this is actually basically calculated from the either radiation pattern or something like that, and EVM. So that we will talk later. EVM and modulation accuracy. So that is what modulation accuracy means. EVM. I'm sorry. Actually, it should be EVM should be a subset of this modulation accuracy. Okay. Then occupied bandwidth is, so what bandwidth is being occupied, it should be within that limit. Okay, otherwise you are not occupying the other bandwidth also, or you are occupying very less bandwidth, that also need to be done. And a spectrum emission mask, it's kind of extended version of ACLR. Okay, so ACLR defines only simply adjacent channels. Okay, so beyond this band it will call it as adjacent channels to certain bandwidth. What spectrum emission mask will do is, see, you will in this band you will have this much power. In this band you will have this much power. In this band you will have this much power. This band you will have this much power. For example, this is 23 dB. Yes, minus 30 dB, minus 50 dB, minus 80 dB. Something like that. Similarly, to replicate this side. Okay. So this is called as spectrum emission mask. So this masking is done. Your spectrum should be within this one. Okay, it should be something looking like this. Okay, if you capture the signals, it should be within this, like this, something like this. Okay, and receiver capabilities like sensitivity, sensitivity. So what do we generally we look for is sensitivity, and other one is selectivity. Yeah, because sensitivity means what? For example, I'm getting, for example, I can explain with the satellite communication. That is more appropriate, because so you have a satellite, you have a ground station. Okay, it is traveling thousands of kilometers. Okay, then it is reaching the ground station antenna. What happens is, so this power in terms of milliwatts. Okay, but your path loss also, noise floor, we call it as noise floor. Okay, noise floor itself in that milliwatts. And what happens? Then you will not be able to, your receiver will not be able to distinguish. For example, your sensitivity is minus 60 dB. Okay, for example, sensitivity of the device now it is nowhere accepted. Okay, 60 dB for example. Okay, noise floor is minus 70 dB. Then you will not be able to distinguish your signal properly. Okay, so noise floor is minus 70 dB. Sorry, minus 50 dB. Sorry, minus 70 dB. Then you will not think. So sorry, noise floor is 50 dB. I'm sorry, noise floor is 15 dB, 50 dB. Then you will not be able to distinguish, because your receiver will be able to receive the signal comfortably within this range, minus 60 dB. That is the least power level it can receive comfortably. It can decode the signal. Okay, but noise floor itself, it is minus 50 dB in that particular location. Then nowhere it is it will be very difficult to distinguish. I think minus 70 dB. Okay, yeah, okay. Okay, so it should be it should be very it should be as, I think it's minus 70 dB. Okay, so minus 70 dB, because noise floor it is able to distinguish the signal. So it should be highly sensitive, and then the sensitivity of the signal, for example, sometime I'm sorry. Okay, one minute again. Come again with this. Okay. Okay, let us consider this again. Okay, like for example, say you have receiver receiving, so noise floor is minus 70 dB, minus 60 dB. Okay, your signal, actual signal is coming with the power level of minus 70 dB. Okay, for example, minus 70 dB. Okay, noise floor is minus 60 dB. And your signal, actual signal, coming with the power level of minus 70 dB. So now what you will do is, if your receiver sensitivity is minus 60 dB alone, then it will only detect the noise, not the actual signal. Okay, if your device is sensitive to minus 100 dB, okay, you can able to decode the signal, then you can able to catch and decode this signal successfully. So that is called as sensitivity. Next is selectivity. Okay, see, you will get multiple faded signal, but you have to select the right signal. So because for example, you have a device. Okay, this is the system simulator. Okay, system simulator, or node B, you can call it as. Okay, node B. So you are sending the signal. This is actual signal. Simultaneously you are sending the interference signal also. Okay, interference signals, several interference signals. Then the device has to decode the particular signal alone, desired signal alone. You should not decode these things, because it is interference signal, it is an unwanted signal. So that selectivity have to be there. And blocking. Okay, blocking means, see, for example, I think it's somewhat related to even ISA law, spectrum emission mass, selectivity, everything, so interrelated. So it's another subset. Blocking means, see, what they will do. So for example, I say similar kind of thing only, selectivity only. So what happens is, so you are sending signal with some power, okay, actual signal with some power to the UE, okay, but simultaneously there are some interferences are available in the environment. But if that power is high, then what will happen is, it will block the performance, or it will degrade the performance of the device. Okay, because it cannot be able to decode the original signal. Okay, so in the presence of interference signal, how your UE is, for example, throughput, if you are measuring throughput, how your UE throughput is affecting in the presence of interference signal, that we will analyze using blocking technique. So that is, in band blocking, out of band blocking, several things are there. In band blocking means, for example, you have a set of band is allocated for example CV2X, it is 58552 to 5920. Okay, 58552 to 5920. Okay, so the interference is, for example, you will be using, for example, some frequency. For example, you are using 5890 as the frequency. Okay, mid frequency, actually mid frequency 5890 as the frequency, but your interference signal somewhere between this band. Okay, within this band. Okay, that is called as in band blocking. Okay, so I am sending interference signal with a certain power level, for example minus 44 dBm. So I am sending the throughput data through this frequency 5890. I am sending interference signal, for example 5860. I am sending interference 5900. I am sending interference, and 5880. I am sending interference. 5915. I am sending interference. Okay. In the presence of this interference signal, okay, my signal is actually what? 5890. In the presence of other interference signal, for example 5860, 5880, 5900, 5915. In the presence of that, how throughput is affecting, how UE throughput is affected, because it has to receive that packets correctly, but if it is not receiving them, which means UE is not capable of handling that interference. So this is called in-band blocking. If the blocking is from, if the interference is from out of band, which means other bands, then for example up to 26 gigahertz, then it is called as out of band blocking. Okay, that is, next is intramodulation, that we'll see in the some of the slides. Okay, intramodulation, what happens? See, you have frequency F1. Okay, okay, then it is getting combined with the frequency F2. Okay, then it is creating the frequency called F3. Okay, so this F3, for example, falls under any operating bands. Okay, any, for example LTE bands, for example LTE network is coexisting with that CV2X network or 5G network. So this F3 falls under that particular, for example you are designing for 5G, your device is working under 5G network. Okay, it is creating intermodulation product of, for example F3. Okay, that F3, for example that F3 matches with the LTE frequency, then what happens is it will degrade the performance of the LTE network. Okay, so that is called as intermodulations. Okay, so next is measurement parameters. So now, so far we have seen some overview of for basic component capabilities, and what receiver has to be, how receiver point of view, what are all components to be verified. So those kind of stuff we have discussed now. Next we will go for different subsets. Okay, so in detail. Okay, now measurement parameters. So now we will go for measurement parameters. So measurement parameters in the sense, see, first one is power. First foremost thing is power. Okay, so if power is proper, then we can go for further analysis like modulation and throughput analysis, performance analysis. Everything we will we can able to measure. Okay, so first and foremost thing we have to measure is power, because if a UE is not sending that power, capable of either transmitting or receiving certain power level, sensitive to certain power level, then there is no use. Okay, there is no use of proceeding with other things. That's why they always check with power first. Transmitter point of view, and I'm sorry, I think some messed up. Okay, okay, so something messed up. Okay, so first and foremost thing what we measure is, okay, so so transmitter point of view, it is first and foremost parameters, effective isotropic radiated power. Okay, so how it is mentioned is like how, so what definition is that you have isotropic antenna that radiates. It's a hypothetical antenna that radiates equally in all the direction. Okay, you have for example some antenna, okay, for example horn antenna, okay, horn antenna, horn antenna, it is radiating like this, okay. For example, its gain is for example 50 dB, okay. And so now effective radiated isotropic radiator power means what? So if I supply the power, input power, so what should be the input power of this particular isotropic antenna, and what should be the power that is should be supplied to the isotropic antenna in order to get the pattern like this, okay. Isotropic always equally radiates in all direction, okay. But the maximum power level here it is 1 dB, it should be 10 dB, for example 10 dB power. So this horn antenna gain is 10 dB, okay. So in order to get in order to get that this kind of radiation pattern or gain of this much, so what should be the power, what power should be supplied? That power is called as effective isotropic radiator power, okay. Effective isotropic radiator power. So once again I am repeating, so you have isotropic antenna radiating equally in all directions, okay. I repeat. So see, you have isotropic radiator antenna, isotropic antenna, isotropic radiator, okay. It is that equally radiates in all directions. You can see that it's kind of circle, okay. So you have a horn antenna, okay, for example horn antenna, so it is radiating in this fashion, green color, okay. So here the gain is, for example here it is 1, here it is for example 10 dB, okay. So 10 dB, the pattern is like this, okay. So what power I have to supply to the isotropic, okay, which means effective isotropic radiated power. So the definition itself clearly says that, so what power I have to supply to isotropic antenna in order to get a pattern like this, yeah, something like this, okay. So in order to get this kind of this kind of pattern, or this much power, actually I have to get basically I have to get this much gain. In order to get that, what should be the power to be supplied? That is called as effective isotropic radiator power. Next is total radiator power, okay. Total radiator power in this sense, it's integration of all the power points, okay. So as we mentioned in the last presentation, you have a spherical coordinate system, okay. You have a spherical coordinate system. So consider this as a ball. In ball, each grid points, as I mentioned in the conductive OTA measurement setup, each grid points you will capture the power level, okay, power values. Then what you will do, you just integrate the values, all the power values in appropriate manner, then you will get the total radiator power, okay. So basically we used to, so in test you might have seen EARP for theta plane, EARP for phi plane. Based on that, then we will integrate both of them, we will add both of them and then integrate, we will get the total radiator power, okay. Next is max power, maximum, what should be the maximum power? For example 23 dB means it should be it should not be beyond 23 dB means it should be about 23 dB power. For example class 3 devices say maximum power should be 23 dB, okay. But what happens is, if you are using partial RB, if you are using full RB, it will be less than 23 dB. If you are using partial RB condition, then it will be slightly higher than this, okay. It will be around 23.1 dB or 2 dB. So that they will give some tolerance values as well, okay. The maximum power should be within that tolerance, value. For example 23 plus or minus 1 or 2 dB, okay, they will give tolerance. So the variation should be within that plus or minus 2, so variation within that, otherwise test case will fail. Next is min power. So min power should be, for example if I am supplying minus 50 dB, we have to receive, okay. So if it should not be too much, for example minus 60 or minus 70, there will be some tolerance also. Power reduction, okay. What happens is, for example if I am applying stringent conditions, okay, for example different partial RBs, different RB start, okay. So that time what happens is some power reduction will be there, that should be within the limit. That's what it talks about. Next is antenna power error. I think antenna power error, see, you are feeding into the you are, I think I thought of going through, but okay, somehow, okay, that's fine, okay. So and antenna power error is like you are feeding input to the antenna, okay. So now your systems are all working fine, But if antenna does not work properly, then the power will be wasted. Okay, and also if it the whole RF chain has to be perfectly matched with the antenna. Otherwise, what happens? You will get a what happens? You will get a mismatch power. There's a lot of reflections will be there, so that therefore the effective power radiated from the antenna will have a problem. Will have there will be some effect on that or reduction. Okay, so those kind of some error will be there. So those kind of things can be measured here. Transmit off power. Okay, transmit off power. Off means when I am when I am switching off that particular channel. Okay, particular. Though there the power level should be whatever is mentioned in the spec. Okay, for example, minus 50 dB if it is in on condition, minus 50 dB means it should be minus 50 dB or within that. Otherwise it should not radiate, because sometimes we also might encounter when you switch off the light, older lights and all, when you switch off it will take some time to completely switch off. Okay, because that is the because the capacitors are there, several inductors are there, that is storage device, it needs some time to discharge. Okay, so transmit off power also something related to that. Okay, so when you are switching off, okay, you are ensuring that it's off in that particular channel, but it should not radiate anything beyond certain power level. What happens is, if it radiates, then it will affect the other devices or other spectrum. And on off power. Okay, when you are applying both on and off simultaneously for one band, within the bandwidth, one particular band you are bandwidth you are sub bandwidth you are switching on, the other bandwidth you are switching off. So on said there will be a certain power level will be there, it should meet there, and off there should be some power level will be there, it should meet there. Okay, next is modulation accuracy. So that's where I think this should comes under I think modulation. So I'm sorry, so this is come next is spectrum emission mask. I think we have discussed already. It's similar to ACLR we have mentioned. So there will be a mask will be there. So the at each spectrum, for example, here it's x-axis is frequency and y-axis is power level. Okay, so power level, and so at each frequency, for example 20 megahertz if you are measuring, for example 60 megahertz you are measuring, so 10 megahertz is your bandwidth, so remaining 10 megahertz this side and 10 megahertz that side. Okay, 25 megahertz this side, 25 megahertz that side. Those when the emission should be within this limit, otherwise it will be failing. Next is receiver point of view, total isotopic sensitivity and effective isotopic sensitivity. There is one more parameter, effective isotopic sensitivity. Like effective isotopic radiator power, we have effective isotopic sensitivity. In total radiator power, we have total isotopic sensitivity. Okay, next is that EVM frequency error and modulation point of view, we have to measure EVM frequency error, EVM spectrum flatness, in-band emission, carrier leakage, performance. Okay, performance point of view, reference sensitivity. Okay, and in-band blocking, out-of-band blocking. This I think we have mentioned. So reference sensitivity means, for example, you are sending you are given cell power as the cell power or node B output power. Node B is transmitting with the power of, for example, minus 110 dB. Okay, dBm per subcarrier. Okay, that time if I am sending signal with that power level, UE must be able to decode that. So if UE is not sensitive to that power level, then sensitivity is very poor, then it cannot be able to decode that. So what happens is your throughput will become drastically down. Okay, so that is what we measure here, reference sensitivity. And demodulation of PSSCH. Here what we will do is we will apply the fading scenarios, and then different fading scenarios, and then different scenarios like different fading scenario, then we measure the throughput. And AWG noise, we will apply AWG noise as well. So several things we will apply, and then we will measure the throughput. So we will apply the fading scenario, Doppler shift and AWGN, and then we will decode we will be able to we will apply all those scenarios, then we will we will see how UE is decoding the device. For example, from the node B, we will send all these fading scenarios, fading, AWG noise, and then a fading AWG noise, and then Doppler shift. So we'll apply all those stringent conditions and along with our signal. Okay. So then whether UE able to decode the packets or not, how many packets it can able to decode successfully, that throughput will measure. And similarly this one, and spurious response is nothing but your spurious response means, see, your spurious frequencies. I think intermodulation products will create several spurious frequencies, because you can, if you look at the spectrum, wide spectrum, okay, if you connect with the spectrum analyzer, you will see a lot of frequencies, a lot of peaks will be available. Okay, apart from your for example, you have this is your desired signal, but apart from that you will see a lot of peaks available, okay, at certain power level. So with that power level, it is coming from node B. Okay, so with that, so maybe spurious responses from your devices, because device also will have signal integrity problem. Then because it is RF devices, several devices are embedded with that system. So several devices emit different kind of frequencies, and that also that will add together, and then we will create intermodulation products. Some will have harmonics. Obviously, RF components will have harmonics. That those some of the two harmonics will add together, and then we create another intermodulation products. And then those kind of things are available. So these frequencies will be available in the environment, or it is coming from the even from the base station to the UE. Okay, so under this condition, what should be the what is the throughput I am getting, whether UE able to decode under this condition also, that I have to check. Okay, so spurious response will not be that much, but still with that power level, with that spurious frequencies, in the presence of spurious frequencies, my UE can be able to decode the my correct signal or not. That things adjacent channel selectivity we already discussed. Next is out of band emission. Out of band emission means, see, UE that's just now we mentioned. So UE will not correctly it will not transmit, like it is not like ideal case, like for example, it will not be straight like this. For example, if you take band pass filter, it will not be, the response will not be like this. Okay, it may be like this. Okay, a practical filter will be like this. Okay, there will be some offset. Okay, there are some guard bands are given, but still it will radiate in other power, but in certain power level, but it may affect the other performance. Spurious emission, I think we just may mention. So how it will happen? Adjacent channel leakage ratio. So okay, adjacent channel leakage ratio, it's actually and spectrum emission mask we have discussed already. Why I am putting both the cases, like channel power also I have put. Actually it's a channel power measurements, but out of band case these are all coming. Intermodulation we have discussed, harmonics we have discussed. Okay, now as per 3GPP spec, and also, so before we start with the 5G measurement, we need to check beam peak, beam to be aligned with the beam peak should be aligned with the UE. Okay, otherwise what happens is, whatever measurement you will do, you will end up in wrong values only. So that's why the initial procedure has to be done. Well, that is 5G initial access and then beam management. Okay, so what they will do, initial attach will happen, and also you will have to ensure that beam peak is directed towards the UE. So for example, you are sending for example, you will send it array of beams, some of the beams, and then finally find out, okay, you lock the beam, which is this beam is beam peak is pointing towards the UE. So then we have to lock the beam. Okay, you can see here beam sweeping transmission, several beams are being swept. Okay, then get synchronized with the, try to synchronize with the UE. Beam system information will be basic information will be sent to the UE. Then it will through a random access channel, then it will receive the node B will listen to the UE and then say that, okay, I got some information from the UE, that this how this is calculated based on the channel state information reference signal. Okay, channel state information reference signal, and also says SSB. Okay, single side block, I think. Okay, so SSBs and then channel state information and reference signal, channel state information, channel state quality information, channel state quality, channel state information, channel state quality, and SSBs and RSRP values, RSRQ values. These are all involved in this process. Okay, so if you Google these for these parameters, because based on RSRP only we can able to decode, because how much is the path loss and other things. But whether UE pointing towards and also based on SSBs and other channel state information signals, so it can able to UE maybe ensure that okay, I'm pointing to the correct node B, okay, because it should not be from other operator node B, okay, that we have to ensure, okay. And yeah, UE, once UE, okay, based on reception, UE is selected a specific being selected beam, okay, because UE will say that okay, this beam I am getting very good signal. Then what you will do, UE specific selected beam will be sent to the UE, that okay, through which you will send all the data, okay, required only for random access response, and system information will be after random access response and then system information. This beam will be locked, okay. Then only this is the procedure you have to do before proceed for any testing, okay. But in other technology like LTE also, there it is cell coverage, so you need not one cell it is covering means that's fine, but here it is beam coverage, okay. So that's why we need to ensure these things in while doing in the 5G signals. And if you are applying even cell coverage point of view, it's not a problem, but when you are applying beam, then it is a quite big problem. So the next is that data control channels can be handled. See, next, once beam is locked, then data and control channels can be can start their job, okay. And that's all. Next is that now conformance testing, okay. So now we will see we have seen several parameters, okay. Now we will see conformance testing, okay. Conformance testing means what? So I have mentioned that there are several parameters are dictated by the spec, and how to do everything is all in what parameters to be considered, what values to be, what is the tolerance, what bandwidth to be used, what frequency to be used, what is the climatic condition to be used, what RB combination to be used, what is the start RB. So all the information will be provided with the spec, okay. So this spec, so based on spec, we need to ensure that whether test cases your UE performing that with that limit or not, that we need to ensure. For example, as we mentioned before, ARP, it's verify the generation radiated power beam per axis for frequency range, and TRP, total radiated power, total isotropic sensitive power, alternate power error, maximum power reduction. So these are all there, okay. So this is the bandwidth I wanted to show you, okay, because I was mentioning that, see, there are several bandwidths terms are available. One is channel bandwidth, okay. Channel bandwidth is this, okay. It is maybe for example, if it is 10 megahertz, you will not use entire channel bandwidth, because that will end up in and there will be you cannot use the entire channel bandwidth whatever is being provided to you. For example, if your operator given 10 megahertz bandwidth, okay, you cannot use the entire channel bandwidth. You have to offset, because your device is, for example, designed for 10 megahertz, but they will say designed for 10 megahertz, but it will not perform equally well in the entire bandwidth. It will be as I mentioned before, for band pass filter, the response something will be like this, but ideally it should be like this. There will not be ideal case will not be may not be achieved in the practice. So that's why, so they always give it some guard band, okay. And you can see here transmission bandwidth is only this much, okay, NRB. So this is the transmission bandwidth configuration. So this is the transmission bandwidth available, but out of which how many RBs we are going to send, that also is there, okay. For example, I can use the entire RB structure, for example full RB, for example 48 RB in the case of 10 megahertz bandwidth, or for a given subcarrier spacing as 15 kilohertz, or I will use only some of the RBs. I can use from starting to first 5 RB, or in between 5 RB, or last 5 RB. I can use anything I want, okay. So under these conditions, what is the power levels are happening? So those things we have to see what power reduction is happening, okay, when I am dealing with this. For example, first 5 RB I am allocating to the 1 UE, and second 5 RB I am allocating to the, for example, second scenario might be 5 to 10 I am allocating. Some scenario I am allocating 45 to 50. So something like that. So what is the occupied bandwidth? Okay, so what bandwidth is being occupied properly? Okay, that we need to see. And power control and transmit time on and off. Okay, for example, see, you are only say, UE is sending active in this particular with the in this many RBs only active. Other RBs not sending anything. So this is called as off. This is on. Okay, so you can see here results. Okay, you can see here for on power it should be 16 point, for example 1.60 dBm. For off power it should be minus 96. So whether you are getting minus 96 or not, so this is the off power. Okay, this is the on power. Okay, you can see clearly distinguished, right? So this is the on condition, this is the off condition. On condition, off condition. So it's meeting the limits. Okay, if it is not meeting the limit, then we have to see what is the problem. Okay, because some UE RF components have problem. Apart from test solution problem, we have to see. Then when test solution don't have a problem, then we have to see in the RF component point of view. Okay, and okay, now you can see that RF components. Next is modulation quality testing. Okay, modulation quality testing, the first and foremost parameter is that error vector magnitude. So let us spend some time on this. So you can see here, okay, your modulation, constellation, we used to call it as modulation constellation. For example, if it is a BPSK, okay, it will be either this point or this point. Okay, if it is QPSK, you will have this point or this point. Only phase is different, non-magnitude is different. Magnitudes are different. So QPSK it is this point. Okay, and so there is no magnitude variation. Magnitude is equal, but phase is 90 degree, 45 degree, minus 130, 135, like that. Okay, but when you are going for a QAM measurement, okay, where the amplitude phase will vary. For example, here one point, here one point, here one point. So here one point, here one point, here one point. Okay, so if you draw a line, so the length of the line dictates the magnitude, and the phase subtended by along the axis is angle. Okay, so for QAM it is different. Okay, for example, in this point, so this angle is different, this angle is different, and magnitude is different. Okay, so QAM is nothing but quadrilateral amplitude. It will in this modulation scheme we have both amplitude and phase variation available. Okay, but in QPSK there only phase variation is available. Okay, so in that case, so any modulation for that matter, for example, my modulation constellation point should be somewhere around here. Okay, but what happens is, due to certain interferences, or due to some power degradation, or due to various reasons, okay, various reasons whatever we mentioned before, so with the due to that, this points is slightly shifted like this. Okay, so shifted like this. Actually it should be here, but it is actually while measuring we are finding that the point is here. Okay, so this is the measured value, this is the reference value. Then you are seeing that, okay, oh, there is a phase error. Okay, the difference between the offset phase error is available, and also magnitude also has some error in phase and quadrature phase components. So in phase means what? So for example, if you are starting your signal like this, okay, then quadrature phase, what will happen? 90 degree phase shift. Okay, it will be like this. Okay, so what happens is IQ magnitude error available, and then phase is also difference is there. So this is called as error vector. So it will have two components, both magnitude as well as the phase component. So this has some tolerance. So you cannot have huge tolerance. For QPSK the tolerance is 17.5%, and you can see that 256 QAM it is 3.5%. Why? QPSK you have only 4 points. Okay, so if 17% is there, so maybe it will be moving like this. Okay, that there is no problem for other constellation points. But if you are having QAM, so as the modulation order increases, the ABM tolerance keeps on decreasing, because in the same location itself you will find lot of points. Okay, so those points those points, so each point, so those points, what happens, for example, if my 17%, if you have a 17% tolerance for it to 256 QAM, what happens is, for example, 17% is here, okay, so for example here 17% may overlap with the other concentration points. You will not be able to decode correct data, okay. You are looking for example this point, but it will be there in this point. So that's why the EVM tolerance is inversely proportional to order of the modulation, okay. And this is the one of the explanation. You can see here quadrature is m of t sin theta sin phi theta pi of t, and in phase is m of t cos. This is the cos axis, then this is the imaginary axis, real axis, imaginary axis, and it comes from this one, sorry, e power j phi of t or so and so on, okay. And so where the real part is cos term and the imaginary part is sin term, okay. So this is the EVM, okay. You can see here. So for example, how they are pointing the EVM polar diagram, phasor diagram, and then if you compare these two are same only, okay. You can see here. So the amplitude gets varied. See, when it overlaps, the signal gets overlapped. When it is moving here and there, then you are getting there is a difference in that, okay. That's what I wanted to say. Next is that you can see here that next performance testing. So modulation quality we have seen. You have apart from EVM, you have frequency error. You need to have it should be within this tolerance. EVM spectrum flatness, carrier leakage, in-band emission, and many more, okay. And you can see here. So performance testing. So performance testing is nothing but as I mentioned, so throughput under various constraints, okay. Reference sensitivity, this we have discussed. Maximum input level, for example, if you are sending too much power also, for example, if BT is sending too much power also, then in that condition also not too much power, but a certain power level, okay, beyond certain beyond the normal power level, and then your UE has to decode the data. Throughput should not be affected. So that also we will check. Power imbalance, okay, and in-band blocking, out of band blocking. So out of band blocking. So then spurious response and so on. So under these stringent conditions, what is my under working? So this is the one of the for example, you can see here. You can see here, see 869 megahertz is the actual frequency, but you can see here some other frequencies being shooted up here. So this is called as passive intermodulation kits modulation diagram. I think I have found from some website, okay, some antenna manufacturing website, where you can see that, see, this is the desired signal, but you are seeing some other signal also, which is due to various things, because for example, antenna is near to metal, near to buildings. When your antenna is mounted on the building, you will get a lot of intermodulation things, because sometimes they will put flex, and then everything will be there, and also the ladder and many things will be there, okay. Under that condition, what is the my antenna performance and device performance we have to see, okay. Next is that out of band measurement. Fourth category is that out of band measurement. So far we have seen first category is channel power, second category is modulation quality, third category is performance. So guys, so first category what we have seen, maximum power and power reduction, all the stuff we have seen, and minimum power. So second, modulation quality, we have seen EVM and spectrum flatness, and then carrier leakage, and so many parameters we have seen. The third one is performance. Performance we have seen, so under various stringent condition, what is the throughput of my device, whether throughput is having or not. Next is that FIG RF conformance testing, out of band measurement, okay. Out of band measurement means to estimate the unwanted emission in the frequency other than the operating band, okay. So out of band emission, so it can be emission or response also, okay. So emission means what is being emitted, like what is the particular device is emitting in other bands, that's what is the emission. So out of band MC, this is what I was telling, spectrum emission mask, okay. So you can see here, this is the desired band, but you are having mask here, okay, mask here. So the adjacent band frequencies spectrum should be within this limit. Otherwise, what happens is if it is coming beyond this, then it will create a problem to the other operating devices. Okay, the spurious response, for example, you can see here. You can see here. So you can see here in-band images active. So in-band emission has images. Okay, because it comes from basically comes from harmonics. Okay, and so this is the active subscriber, but the there will be image frequencies will be there, that is called as in-band images from active subscribers. So this image frequencies will come into picture. If this has a certain beyond certain power level, then it will affect the performance of other user or other device, or even this device also. So that's why these are all somewhat related to intermodulation, harmonics, other stuff. Okay, so intermodulation we have discussed already, and harmonics we have discussed already, and that's all. So thank you for, and in this way what we have seen: device testing introduction, why we go for device testing, and what are all process involved, and then some of the introduction we have seen, and what are all parameters to be measured and how it is being measured, what are all stringent conditions are mentioned in the spec. So everything we have briefed, and we have discussed about some of the parameters, how it is being measured, and what is unique feature of that particular parameter. Everything is measured. We have discussed to the best extent possible, because due to time constraint. So we have discussed to the best extent possible. So thank you very much. If you have any questions, please post here. Thank you. Bye bye.